then, just like for a first order and the second order differential equation, so we have this space of solutions, that the set of solutions of a homogeneous, a linear, well, nth order differential equation is a vector space of dimension n. So the dimension of the vector space is the same as the order of the equation. And then, so more specifically, well, due to verifying that it is a vector space is actually straightforward, and verifying that its dimension is n can be done in the same way as we did for second order equations, by constructing an isomorphism with Rn that uses the existence and uniqueness theorem. So furthermore, for n functions, we have the Wronskian, the concept of a Wronskian, and it is the determinant of a matrix where the first row is the functions, the second row is the first derivatives, third row is the second derivatives, and so on up to nth row, which is the derivatives of order n-1. Then it's very easy to see that if functions are linearly dependent, then their Wronskian is 0. The converse is not true. The Wronskian may be 0, but the functions are linearly independent, so it is possible. But if functions are solutions of a linear homogeneous ordinary differential equation of order n, then just much like for second order differential equations, we have Abel's formula, which is this one, right? So the Wronskian is some constant times e to the minus antiderivative of the coefficient at the derivative of order n-1, right? And then functions are linearly independent, and hence they form a basis of the solution space if and only if the Wronskian is not 0, of course. Yeah, sorry. All right, and then again, very, very similar to the order 2 situation. So we may have a non-homogeneous linear ordinary differential equation, and then the general solution of a non-homogeneous differential equation is a particular solution of the non-homogeneous differential equation plus the general solution of the corresponding homogeneous differential equation. So then, just for your information, there is a method of variation of parameters for an nth order ODE. It's pretty complicated, but it still works. So the final result is kind of very similar to second order differential equations. Well, and then please stop the lecture now and take the quiz.